This talk would be based on what I have done while I was trying to work on discrete-time sliding control, and particularly based on orchestration. There are some very basic assumptions that I have made while working with this. So this may not coincide with the definitions that many other experts would. So the talk would be divided into these sections. First, I'll be talking about the necessity of sliding mode control to be discretized, and then let's go into the topic. So we are in the digital age, so we are going to use various complex devices to implement any control, and sliding mode control would not be accepted. So you have to discretize the control for better implementation. And sometimes we may have models that are in discrete time only, even though what we have to note is theory of sliding mode control has started from a continuous time framework. So if your model is discrete time, described discrete, how do you say how do you work out what should be the control or what should be the sliding mode control? That has to be. Let's see this example, the popular one that was proposed by Gao. You have a continuous time system and you develop a reaching law, which is continuous time only. Obviously, if you want to implement in discrete time, you discretize the law, you do an Euler discretization and come up with this expression. And if this expression is used, then this is the reaching law that can be. And what is that? That is that in each step, the trajectory or this sliding function, it moves towards the sliding surface and never moves away from it. But this sort of a definition may not be enough if you're going in a framework, because you may end up with a motion that looks like this. It is always moving towards the sliding surface, but sometimes they're not going near. You have to modify this in a sense that you add an additional condition so that sliding surface moves towards the sliding constant moves towards the sliding surface at all points of time. And or else what could happen is you may have a situation where it moves again. So this is a well-known reason. And if you implement this, figure out a sliding control with CEFIPRA, it follows all these conditions, you would end up with a situation where, except for a very narrow band around the sliding surface, you would have convergence at all points. But if you are going to use for discrete time, you have this very famous problem of scattering band. You have a sliding band, you have this sort of a control, and you have this scattering. So let me go a little further. Now you have a scattering band. Right. So you have this control, quasi-sliding of control that has this expression. And it can even, if you have an uncertainty in the system, then until it is max, you can modify the control law in a manner that it takes care of the uncertainty also, even though there is modify the law by adding the disturbance itself. The control becomes unprofitable because you don't know what the disturbance is. However, if you take the average of disturbance, you will be able to. So this was the result that was popularized by part of the content. But still, you have the situation that you have this surface being crossed and recrossed again and again. And some conditions, depending upon parameters, you have the width of this sliding mode track. And that is predetermined, that is theoretically even computed, even without implementation, even without actually worrying about whether the delays that you use or the nonlinearities that you use in your implementation, what are properties, what your frequency range. So that begs the question that the problem of catching when we are talking about continuous time system was because the delays were not able to respond at frequency. But while you are talking in discrete time, it is theoretically you always have a quasi-sliding mode track. In fact, there is no way to make this band 0. The only way to make the band 0 is, so if you have this band delta and the width of the band is epsilon tau by 1 minus q tau, and q tau has to be less than 1. The only way to have this band equal to 0, you make it not have the signum term in your country. The equivalent of a 0, you do not have the signal term, you have a basic state field. If you have a state field that you don't converge to whatever point you have finite. You assume that there is a system. So probably the problem is that you had not approximated this most precisely. Probably there is you have this business time reaching law, and this reaching law has been approximated with an oil and was it enough? Should we have gone to the better or a more precise approximation? So if you have a differential equation in S, and I want to find the value of S to an extent which follows this continuous time differential equation. Probably you take one more derivative and find out the second derivative as far as the first equation is concerned, and equivalently represent what is something. But if you try to get the second derivative, you end up with a problem. You find the derivative signum of S, and to go further, then probably you have this issue, or you end up with this realization that the first equation is not analytical with respect to X, which means that you cannot use Taylor series by approximation to get an example. So there is no way that if you go by this approach, there is no way you will be able to ever find a performance by using a discretized version of your implement discrete time study. So that would mean that we need a different approach. Discrete time definitely it's more practical, but then there is always tech. And the other point is that you can have an approach which is completely based on the discrete time model, not based on any approximation of your continuous time study. So that's the easiest way is to take the next step. I could have certain English and to contain sliding function together. So this was another work that was done by the Roorkee and Janardhanan, where you have this nominal control that is being applied whenever is possible, and whenever the required control is more than the capacity of actuator, you apply saturated function. So this would give you one sort of a approximation, but you can originally what you wanted the surface to be in the single stuff like a timeline. But then why even do that? You can either go a little slowly and say in K star steps. If you rather than one step in K star steps, you can reach the sliding step. That was what I proposed by Butterfly. You have a distance, and depending on distance, you have a input where you want your sliding function to follow a known a priori decided function SD, which will not be inside and which will decrease by an amount that is greater than the amount of distance that is presented to something like that. And you have this appropriate. And this will again bring your system to within some bound. All this is good, and all the controls that you have are using the speed and some other factors that is working. But then in the state mode, there is no error. And so there is no the entire state of a system is never there to measure. And the other point is that what is test? If a sliding function and s of t to the 0 or s of t to this surface, but is that measured? The sliding function measurable is the sliding function. Yes, is sliding function equal to 0 means that the output is being flat or the output has is being regulated. or does it mean something else? Let us say if your system is not being on, can the output be your platform? So we should mean that probably you have a system where you have the states and you have an output, but it is not necessary that the output is equivalent to the platform that we want to play. So to use. And the other problem that we had was that you have all your control are based on your states. But you have output. An easy way out of this is to have a state observer. You have a state observer of this structure, you estimate the state. And based on the estimate of the states, or based on the estimated states, you design the control. You x hat instead of x, and that can be improved. But problem is that we could add more dynamic. We are already complicated. And the approach that we had for this is that we are dealing with a discrete system, a discrete time system, and which would mean that it is possible to sample your output and input at different. Now, when you are sampling your output at a different rate, creating fictitiously creating more number of outputs than the number of more number of outputs. It would mean that if you try to this approach that data, you have a system, your input is sampled at a rate of tau, your output is sampled with a sampling time that is n times faster than the input. And you are stacking the output and designing the control. You have a system like this. Then you have a continuous time system, and then you discretize. Then you are stacking this time. Now you take the first two equations. You have a state equation, and in your output equation, you have the output matrix. So to say, to C0, it doesn't have a single word, it has multiple words. It would mean that it is possible that the state can be described as a linear combination of this stacked out and the input, something that is there in the last equation. You can use this equation, this sort of a way to sample the output faster than the input, and then use that generate a control, and that can be used to design the sliding motor. Now, if you use this sort of an approach to design a control because the sliding motor, then what you have is an expression of a control that looks like this. Now, because we have an uncertain system and we have approximated the output from partial information, we did not have disturbance information, still we try to figure out the combination of the state from it. You may end up with a scenario where the band that you're talking about, the band that you have, using this multi-rate sort of output, may turn out to be more than the band that you have if you had UC. But now that's a compromise that you don't have state, this is the best that can. But then, is it really necessary? Here what we are doing is that we are saying that system states are represented as a combination of the output and the trigger. But is it really necessary to we do so much work? So you want to implement this control. Is it necessary that you find this thing to go more deeply? You have a control that is a scalar, which probably depends upon two scalars, f times xt and this sum. So if you can actually estimate fxt and t transpose xt and not necessarily take xt, maybe will be manage it with a simpler solution rather than a solution that would require you to sample the outputs much faster than you. Maybe you can do it later, but what is the result and how do you know that it will actually work out? Let's look at the condition. So, look at that. The CV of matrix that you have looks very, very similar to the other matrix. Because it is the you generally look into, you generally encounter it. This actually means that you are able to estimate from your output, you are able to estimate all this. If this is not satisfied, you are not sure whether in all situations you will be able to use the output, you will be able to decipher what the states are. Because it can happen, there can be two state trajectories that will lead to the same. But what if you don't? So the condition that you have for observability would be the test matrix, the C0 matrix, the full rank. The rank is equal to the its rank being equal to the number of that are not number of number of states that have. Now you don't know the states, so the rank need not be. What it should be is the whatever you want to estimate, these two functions f phi tau and theta. Those two need to be expressible as a linear property of both of C. What are both of C0? They are not C0 times x or C into x is the output of the system. So what you are basically saying is that from the output information, you are able to figure out what these two functions are. And since you are able to get only these functions, you can use them to design it. So this basic concept we had worked on various different systems. And you can sort of come up with a control that looks like it. And also, the same concept of not associating Discrete-Time input with continuous time. We had also worked on other levels of sliding mode control, higher order sliding mode control, where when you're talking about sliding mode control, the second order sliding mode control, and you say that the sliding function and its derivative are both continuous and go to zero in a finite amount of time, then we will explore what continuity is in the context of it. And similarly, if you have a stochastic system and you're talking about sliding on the full stochastic system, you're still working on it and you're interested in that. I'd like to end my talk here and I respect the Professor there for guiding me start this work. And
so we are open for the questions. Audience. Any question from the audience? No. Thank you for the presentation. Interesting. What do you think? What is the price when you avoid observer and starts to estimate it from collection of output measurements? What is the price to pay for such a solution?
multiple measures. There is a possibility that each of those measures is corrupted by noise. Intuitively, it may seem that more noise comes into the system is going to give a worse performance.
But what is about robustness with respect to noise? Because if you do an observer, it can filter the noise. Can filter the noise and make it like smaller in estimates. Well, here each time you just collect measurements with noises.
So, in an observability filter, I can do a filter here.
No, but if there is noise, it's another story. Life will be very simple. Very
I can assume there is some stochastic noise. Assuming there is noise, the stochastic doesn't have any dynamics. An observer without dynamics, but still it can handle.
Yeah, of course, probably. But I mean what sensitivity.
I don't see the difference. But observer, see, what I see is that when you're observing the basic motivation is that what is the reason that you're observing? If the further, then probably an observer would be equation before make a decision on what the state is or what the function that you are observing.
Thank you.
Long live India and France friendship.